Hello, everyone. It's so delightful to see each and every one of you. I see my entire life zipping right in front of me as I look at you. I've been here 53 years, believe it or not. I was here for the inauguration and was an integral part of the activities that took place. And I can tell you there was a lot of excitement um, by Professor Shah and Jim Gear and all the students. We were in charge of getting all the equipment and all the displays, all these signs that you saw. We were putting all of that together and having the opportunity to meet the who is who in earthquake engineering at the time. You can't imagine what a wonderful opportunity that was. That was really unique. I was asked by Greg to talk about earthquake hazard and risk modeling that we did at Stanford. So I'm going to take you a little bit through memory lane, and Haresh and Greg sort of set the stage, as we did Eduardo, about some of the early work that we did on earthquake hazard analysis. And I will start by looking back, and what I recall were the triggers for starting the John A. Bloom Earthquake Engineering Center. Just before I came to Stanford was the 1971 San Fernando earthquake that caused damage to a lot of the buildings that were supposed to be designed for earthquakes. And that created a lot of excitement, in quotes excitement, rather concern among the structural engineers. And I could hear Haresh and Jim Gear and Ted Zuti talking about the changes that will need to take place in the building code. But while I was here, shortly after I came, in December 26th, 1972, was the Managua, Nicaragua earthquake. And to me, that was the trigger of a series of studies on seismic hazard analysis and seismic hazard mapping. Earlier, Haresh mentioned that Banco Central de Nicaragua provided some funding for doing studies in Nicaragua, and they actually asked us to develop a seismic code. But to develop a seismic code, we needed to develop a seismic hazard map. So we embarked on developing a seismic hazard map. But the first seismic hazard map was developed, I should mention specifically, a probabilistic seismic hazard map was done in 1970 by Professor Luis Esteva, who was present at the inauguration, by the way. Following his lead, in 1973, before we even got the funding for the study in Nicaragua, Francisco Silva graduated from our program, and he completed the first probabilistic seismic hazard map for Chile. Following his example, we commenced building a seismic hazard map for Nicaragua. And I do want to emphasize that Chris Morga, where are you? Oh, he's not here yet? Jeez, shame on you. He was supposed to be here. I saw him last night. He was the lead of this project, and there were a lot of challenges. They're still the same challenges are here today, but our challenges were particularly great because there was very limited earthquake occurrence data for the region. There was no ground motion attenuation function. We had to figure out how to model the subduction zone as a dipping plane. Mind you, there was a study done in the mid-2000s by, I will not name who, that still modeled the subduction zone as a simple line. I don't need to say how erroneous that is. Anyway, the success of that map was the trigger for series of mapping efforts that followed. I should say Professor Zuti and Professor Shah and Gear, together with Chris Morga again, developed a seismic code that they delivered to Nicaragua. I should also mention one other thing, that the Nicaragua earthquake was also the trigger for the fall of the government in Nicaragua. And we often refer to it that earthquakes don't only bring buildings down, but they also bring governments down. And Nicaragua is the example where the government fell not because of the earthquake, but it was it made it so much easier for the Sandinista to come in. So following that effort, I decided to do my dissertation on seismic hazard mapping of California. And I would say that this was done about a year before Algermison and Perkins developed the nationwide probabilistic seismic hazard map. And I still remember giving a talk at USGS about the probabilistic seismic hazard map, and they kind of told me that I should go to Las Vegas, beat my probabilities. Lo and behold, a year later, there was a probabilistic seismic hazard map of the entire United States. Oh yes, I did have quite a few challenges, but I think we somehow overcome these in one way or another. Haresh mentioned earlier that we looked at all of Central America, and indeed, we were involved in developing the seismic hazard map of Costa Rica, which was commissioned by the government of Costa Rica. That also was accompanied by the development of a seismic code for the country, which served them really well for quite a few years. The earthquake in 1976 in Guatemala was the trigger for the development of a seismic hazard map in Guatemala, followed by an earthquake in El Salvador that we also developed a seismic hazard map for El Salvador. Honduras was a different kind of trigger. And a company from Switzerland called Motor Columbus came to us and asked if we can help them with the characterization of ground motion in El Cajon in Honduras. They were about to build a hydroelectric power plant and a dam in El Cajon. And we said, well, how about it if we develop a seismic hazard map for the entire country? And that was a different trigger for developing a seismic hazard map. So you can see that we kept going around and followed Haresh's vision of creating hazard maps for developing countries or countries in Central America, one in South America. There were also developments that I don't have really time for, but there were developments for Algeria and Morocco, North Africa. Where's Fuad? Oh, he's right there. He was in charge of for developing hazard studies in Algeria, right? And I won't go into some of the adventures in Algeria. That's for another day and another time. But we were getting a little tired of developing seismic hazard maps, so we looked at it and said, well, what are some of the more interesting things that we have not looked at? And I yanked Thalia Nagnos out of her structural analysis class, as she would say, that apparently petrified her as to why am I singling her out. But I wanted my very first student to be my very first PhD student when I joined Stanford to be also a female. And there was only one other female student at the time, and that was Thalia Nagnos. And I said, okay, Thalia, how would you like to do a PhD and do work with me? So, and we started looking at the next developments for earthquake occurrences. Up to that point, all of our efforts were based using the Van Mark and Cornell model on Poisson earthquake events. And we recognized, of course, that large earthquakes are anything but independent in time and space. So at the same time, in 1980, Shimazaki and Nagata came with their hypothesis for time-predictable and slip-predictable occurrence models, and we used their developments, their proposal, to come up with the so-called time-predictable and slip-predictable earthquake models using semi-Markovian stochastic processes, and that resulted in the two papers that Thalia and I developed in the 1983. Suzuki, who followed suit, extended that, looking at Mexico and the subduction zone off the coast of Mexico. And that led to a wonderful collaboration with Professor Rosenblut at UNAM following the Michoacan earthquake. Kim Lutz actually followed that suit by looking at not just the time dependence of earthquakes, but the space dependence, where an earthquake occurring on one segment will increase the likelihood of rupturing adjacent segments. And that hazard modeling went on and on and on, and I won't go into more details. There were models for aftershocks and force shocks and so on and so forth. But in the 17 minutes I have, I want to move on. Today, we talk about using geophysics-based models for predicting the ground motions. Well, looking back through the long list that Tarja mentioned of reports, the very first geophysics-based model that was done right here at the Bloom Center was by Marty McCann. Where are you, Marty? Somewhere here. But he actually used the normal mode method to come up with estimates of the ground motion at the site. Suzuki followed that same suit, where I recall he used something like 80,000 modes for the Earth, for the entire Earth, to try to represent the ground motion at a particular site. So these were some of the early on studies of ground motion characterization based on geophysics models. And of course, the level of sophistication that we have reached today, I think Jack Baker can tell you, because he's intimately involved with many of these studies. Talking about ground motion studies, and Jack Baker, he and his group have been working on ground motions continuously over the years, but I'd like to bring out specifically the work that has been so impactful for the dynamic analysis of structures, and is now used for widely for nonlinear dynamic analysis and design, and it's become part of the seismic building code. In particular, he proposed the conditional spectra for conditional mean spectra for selecting ground motions, as well as for scaling them appropriately at the periods of the structure. Selecting those ground motions has enabled engineers to conduct nonlinear dynamic analysis, such as the incremental dynamic analysis by Bambatsikos and Alan Cornell. The impact of these studies have been tremendous, and over the years we have seen the impact of many of the studies at the Bloom Center being directly on seismic codes, seismic developments, as well as the insurance industry, as Haresh mentioned earlier. Seismic hazard mapping has been key to earthquake-resistant design nationwide, but it has been now become the norm worldwide. You see seismic hazard maps being developed everywhere around the world, and the GEM Foundation is probably one of the key developers for these maps nationwide. And I have to say, looking back in working on these seismic hazard mapping efforts, we just did it without really thinking that it will have such a lasting effort. Current Stanford faculty, students, and everyone else, postdocs, continue to make significant contributions in the arena of hazard analysis. What I want to mention is the latest seismic hazard map, the 2023 hazard map, has Stanford faculty and alumni intimately involved with the process. Jack Baker is involved with the hazard mapping, but Nico Luco is actually the lead of the National Seismic Hazard Map. Let me quickly move on to some of the risk studies. And I will go back to ATC 13. There were risk studies even before ATC 13 at the Bloom Center, but I feel that ATC 13, this was a very close collaboration with ATC. I see Chris Rajan, my partner in crime. ATC 13 was really the pivotal study in developing an overall methodology for loss evaluation. I remember sitting with Chris and Roger Scholl and Rick Nutt until the late hours, identifying the various components of loss studies and the trying to address some really difficult issues like how do we get damage functions? We're talking about how do we capture the downtime that it takes to repair structures. And as a result of these long discussions, we came up with a rather unique approach known as expert opinion, which you can imagine in the 1980s, using expert opinion was a big no-no. It was just absolutely ridiculous to do that. But we did well go ahead and developed damage functions for all the different types of structures. There were 48 building types and 32 other structural types, using expert opinion, and created a lot of controversy and discussion and criticism. The downtime functions were also based on expert opinion. I got a lot of flack about my expert opinion. You can see I'm used to getting a lot of flack about a lot of things that I do. However, I would say that because this study was so unique and identified so many problems and so many issues, I feel that it was the impetus for houses. And I won't talk about houses because Bill Holmes is going to talk about houses. But houses came in, used whatever issues were raised by ATC 13 and tried to address them in greater detail. In the remaining 3 minutes that I have or so, I'm just going to quickly go over some of the other firsts that were done at the Bloom Center, such as the very first analytical fragility function. After doing the expert opinion, I said, but we are engineers and we know enough about the nonlinear behavior. We are lacking nonlinear dynamic analysis software. And in fact, at the time, in 1990s, mid-1990s, the only dynamic analysis program for structures was Dyna 2D, if any of you remember that. But using that program, we were able to develop the very first fragility functions. I should give credit to Ajay Singhal, who did all that work. This was for low, mid, and high-rise structures. Okay. Then to address some of the issues with the downtime, we looked at assembly-based vulnerability. I should say Keith Porter was the one who had extensive experience in practice, who had looked at and said, well, how about if we look at the sequence of repair events and the various trades that come in and how long it would take for repairs to take place. Simultaneously with that, Professor Miranda and a whole slew of his students, there were about 5 or 6 of his students. I'm listing only one because I didn't have space to list all the references. But there are a whole slew of students who worked on the various component repair issues and the time that it takes to repair. And that became part of the component-based vulnerability assessment, very important in critical studies. Now, the time-dependent occurrence model, we said, but it's not just the time dependence of occurrences. As our buildings become older, they become more vulnerable. So Michael Peck and I said, okay, how can we capture building deterioration and component deterioration? And we were fortunate to have a student like Anirudh Rao to take the lead and develop a model for time-dependent fragility functions, where we demonstrated as the corrosion in a concrete column increases, so does the fragility. So as you can see, things move on, and of course, there's so many other studies, and I apologize to all the researchers that have worked in that area that I've not included, but I need to move on to my last couple of slides. I do need to mention all the work in lifeline risk assessment. Going back to the very study by Hector Manson, who came from Guatemala, speaking about bringing students from around the world. This was from Central America, from Guatemala. He worked on spatially distributed systems. We followed suit with Nez Bashos, who's here, a collaboration with Jim Moore from USC. This was an effort through peer, Jack Maley. Where is he? He's not here. He's there. Hi. You remember the work we did with Jim Moore, looking at risk assessment of lifeline systems, followed by the work of Sturgio, again in collaboration with peer, supported by peer, and then the series of work done by Michaela Miller, Silva Lopez, and Sanchez Salza, working with Jack Baker, with the last one contributing to optimizing retrofitting strategies where you include actually the network analysis of the system. Particularly, I want to, related to lifelines, I do want to mention the work of Renee Lee, who's here somewhere, that demonstrated that if we do include temporal and spatial ground motion and damage correlation to spatially distributed system, your loss estimation can be greatly affected. Okay, and I have some concluding remarks, so I hope I'm close enough to my time. Earthquake hazard and risk studies at the Bloom Center have made significant impact to the engineering profession in terms of hazard mapping and in terms of development of seismic codes. And today a lot of the seismic codes have components that have resulted from research here at Stanford. The implications are also to decision makers at local, state, and federal governments, to the insurance, reinsurance, and financial industry, having several companies founded from the Bloom Center as well as from outside of the Bloom Center. The textbook by Professor Baker and company, Bradley and Stafford, is now probably the most comprehensive textbook. I would say Jack is followed in his grandfather's steps and father's steps, Benjamin and Cornell, to create a book, in this case, on hazard and risk analysis. The impact of the earthquake hazard and risk modeling for earthquakes has been adopted for different types of other extreme events, and we have seen many of the modeling components being applied to hurricane, flood, tornadoes, wildfire, and climate change. The research continues and expanding into resilient, sustainable, and smart communities. And I want to thank all the researchers and all the colleagues and collaborators who have contributed, and thank you very much.